All right, video 5 for Google Form 5 on simple harmonic motion, period, and frequency of simple pendulums. And I don't think there are any pictures of pendulums, but a simple pendulum is really just there's like some ceiling or some vertical surface. Let's go along here. There we go. Oh, I guess that's not making a straight line. That's fine. And really, you just have some string. Often it's said that it's a lightweight string of length L. It's a little script L. And there's this part called the bob, the bob of the pendulum. It's just some object of some mass. And since the string is lightweight, really all the mass is in this bob, and it's pulled up kind of some angle from this equilibrium position. So at equilibrium, it's kind of just hanging out here. So it's pulled kind of some angle theta. So unlike our mass attached to a spring, instead of getting pulled or pushed from the spring's equilibrium point, whoa, that was kind of weird. The spring's equilibrium point, some kind of position or distance x, where maybe we have it here, some position or distance x, that's really the amplitude. Instead of having some distance x, we now have like an angular displacement of theta. And kind of looking at our equation sheet, this is just kind of like our last one. We still have simple harmonic motion. We still have frequencies and periods for it, the time for it to kind of do a full kind of oscillation or cycle. But now we have this pendulum equation, and I've kind of rewritten it here. And the trippy thing kind of looking at this is that, does the mass affect this at all? Well, looking at the equation, I don't see an m anywhere. So that tells me that no, the mass does not affect it. And maybe you're going, well, wait a second. If the mass doesn't affect it, you're saying I could have like a 10 million pound like bowling ball here. So 10 times 10 to the 6. We'll use SI notation here, or units, so we'll put kilograms. No, it doesn't affect it. It could be 1 kilogram or 10 million, because sure, the 10 million one is going to have a lot more force pulling it down, but it also has a lot more mass. It has a lot more inertia that's going to make it harder to change the motion of it. So yeah, it's going to take a lot more force really to get that thing moving quick, but there's so much more mass that it really balances out. So the acceleration is the same, kind of thinking about it in terms of Newton's second law, but as a giant mass, but really this A is just gravity. It's just going to have like it's going to take a bigger force really to get it accelerating more. So no, it really just kind of balances out. You could think of it on the upswing as well. Sure, this thing has a lot of mass that's moving now, but it didn't get accelerating as much in the beginning. So kind of weird, but the mass does not affect it. So we got this great guy here. He's got this terrific, beautiful face. And you realize that, well, there's no A in this either, so the amplitude doesn't do anything. The mass doesn't do anything. Neither of those affect the period of a pendulum in simple harmonic motion. So I've kind of started our first one here. We have a 10 kilogram mass, oscillates at a small angle. Now this is from the videos actually. I think really from our videos they say that theta is less than or equal to about 20 degrees. It really works fairly well up to larger values. But really, as long as it's within this small angle kind of assumption or approximation, it tells us that, hey, this equation right here is going to do a really darn good job of kind of giving us a period for it, or an ability to calculate the period. And we have some light string of length 10 centimeters. Now that's the length, but we actually cannot have that in meters. And maybe you're going, well, why can't we have it, or we have to have it in meters? Maybe you're going, why can't we have it in centimeters? Well, if we think about it, this G right here, G is 9.8 meters per second squared, or in other words, 9.8 meters per second per second. The units have to agree. That's really the main reason why. We can't have centimeters in the top thing and meters in the bottom. We're going to get some crazy bogus number that doesn't really mean anything. And it's just asking us, what is the period? Well, what is the period? We just have to plug into this equation. That's all we have to do. So the time for one full cycle for the period of our pendulum is 2 pi times the square root, and there's 100 centimeters in 1 meter, so I have to move it 2 decimal places. In other words, I'm saying that 1 meter is 100 centimeters. So to turn centimeters into meters, I have to make 100 become 1. So I go take this decimal and I go 1, 2. So now it's in meters. So I did the same thing here. So I have 0.10 meters over 9.8 meters per second squared. And then I just poke this into my calculator. So I do 2 times pi times the square root of 0.10 divided by 9.8. And I get 0.63. And I say use 2 significant figures. So really my answer could be 0.63. And this is a period. It's an amount of time. But it says do not include units. So if you put seconds, that is the correct units. But we can't have that here or the Google form won't know to grade it correctly. But you could have also written as 0.63 because that also has 2 significant figures. And that's really it. If you're someone that's going, well, I don't have like a nice sweet calculator at home, Mr. Johnston. Well, you can go to Google Calculator. It does a pretty darn good job. So we go, well, we're doing that whole 2 pi thing. So 2 times pi times, and then the square root of 0.1 divided by 9.8. And I close my parentheses and I hit equals, and there I go, 0.63. So Google Calculator still totally works. But let's just keep moving on with that then. So our second one here, we have a 2 kilogram mass. So we know the mass, M, and it's oscillating again, small angle. That's kind of important. Light string, so it's not going to affect the period. All the masses are in this 2 kilograms. And they tell us now the period is 0.78 seconds. What is the length? So now it's asking not how long does it take to kind of do a full loop and back. It's saying, well, we know the time to go from here to here. How long is this thing? That's really what we're asked for. So I'm going to do a little algebra just off here on the side because really that's all this is. And then it's just calculator time again. So I'm going to go over here on the side. I need to solve for the length. So if I'm using this equation here, I have my period for a pendulum is 2 pi times the square root of the length over g. Well, I need to divide by 2 pi on both sides. So if I divide by 2 pi on both sides, well, those 2 pi cancel out. So now I have it again. And if I want to get the L alone, you need to square both sides now. So now if I square everything that remains on this side, I got to square everything on this side. So now I'm going to get the period squared over, well, 2 squared, that's 4. Pi squared, well, that's pi squared. And that equals L over G. So now how do I get rid of the G, or essentially how do I get L alone? Well, I times by G on both sides. So if I times by G over on this side as well, the G's cancel out, and then we have L alone. Or maybe you've heard me oftentimes say it this other way, that, well, we're just going to multiply G over to this left side. So really, I have G times the period squared over 4 pi, and I forgot my squared and my pi there, squared equals the length. And so they gave us the length. I think they gave us everything we need. So we have G times the period squared over 4 pi squared equals the length. So putting in the numbers first here before the calculator, I have 9.8 meters per second squared times, and the period is 0.78 seconds, and that's squared. And then we have over 4 pi squared. Now, here's the cool thing. Because I included units, well, seconds squared, that's a second squared then, and then we're dividing by seconds squared. That cancels. The units that remain are meters, so this kind of checks out. Whatever the heck this number is, it's going to be in the right units I want at least. So I'm going to go and put in 9.8 times 0.78 squared divided by, and then make sure if you're doing this on the calculator, you probably, I'd say the easiest way is just put parentheses around this. So then divide by, and then parentheses 4 pi squared. And I get 0.151. So 0.151, well, that's 3 significant figures. So we want 2 significant figures. So I get 0.15, or let's use purple for our answers, 1.5. And the length, we said it's meters, but we cannot include units here. You could have also written it as 0.15 though, because that still has two significant figures. So home stretch, we got two more. We got a 0.1 kilogram mass. We know the mass. Small angle, light string, cool beans. We don't have to worry about those at all. We have a length of our string of 10 centimeters. That's our length. But really, 10 centimeters, that's the same as 0.100 meters. And then what is the frequency of the pendulum? Ooh, that's kind of sneaky. Well, this we're going to have to use two of our equations. We could find the period using this guy right here, but then if we know the period, then we got to plug the period into this one up here to solve for the frequency. So this is really just a two-stepper, but the first step's pretty easy. We just find the period. So first step, we'll just plug in time period. We're just going to use the equation. So 2 pi times the square root of L. The length is 0.100 meters over 9.8 meters per second squared. Well, actually, this is the same exact question we did earlier. 0.1 over 9.8. We already know the period here. You maybe even thought about that when you already did this. We should get 0.63, but let's double check. 2 times pi times the square root of 0.100 divided by 9.8. I get 0.63. Perfect. So 0.63 seconds. Now we just need to use that other equation that the period is 1 over the frequency. Or in other words, kind of doing the old switcheroo with these two, we get that the frequency is 1 over the period. So really 1 over 0.63 seconds? Well, 1 divided by 0.63, that gives me 1.587. So that equals 1.587, blah, 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 blah. And it's 1 over seconds, which is really like cycles per second, but cycles isn't really a unit. It could be like oscillations of a mass. It could be like revolutions of something on a wheel or a tire going around. So we're just going to say hertz, because hertz is just like the number of like cycles per second is what that really is. But again, we want 2 sig figs. So this is 1.6, and there is no other way to write that one. So now our last one here. We have this 0.2 kilogram mass oscillating on planet X. Whoa, we're on a new planet. We have a small angle. We got some light string still. We're given the length. Ooh, it's even in meters, so that's nice. A little less converting. And we're told the period. What is gravitational acceleration due to gravity? Well, that's kind of redundant sounding, but okay. Gravitational acceleration on planet X. Well, looking at kind of our equation, we have that the period, we have that the period for a pendulum is 2 pi L over G. So really, if you wanted to make the period, kind of here's a unique way to think about it actually. Maybe this will help with a test question later. But if you wanted to make the period for a pendulum longer, you wanted to make it take longer for that pendulum swinging here to come all the way back to the same position, there's really only 2 things you can do. We can't change 2, we can't change pi, but if we made L get longer, that means this number is bigger. So this number on top is bigger. That's going to give us a bigger period. So a longer string is going to give us a longer period. All right? Or what's the other thing we could do? Well, we want to make this whole right side bigger. So the only other thing aside from making L bigger is to make G smaller. So in other words, if we made G a smaller value, so gravity's weaker essentially, instead of 9.8, maybe it's half of that, maybe it's like 4.9 or something, then that would end up giving us a bigger number here on the right side still. So in other words, if you went to the moon, gravity is weaker. I'm blanking on how much weaker it is by right now. But since gravity's weaker on the moon, your period would take longer there. Or if you went to a planet that had stronger gravity, a pendulum would swing faster actually, as long as you kept the length the same. So really, this whole question isn't so conceptual. It's just asking us to find G. So doing a little algebra again, we have this periods equals 2 pi square root of L over G. I'm going to divide the 2 pi over. So now I have the period over 2 pi is equal to square root of L over G. Then I'm going to square both sides. Okay, and let's make up a little more real estate here. There we go. That's better. So going from there, and let's kind of clean this up a little bit. There we go. Right there, and then we move it to there. Okay, so we can kind of go step by step. So now if we square both sides, we have whatever the period squared is over 4 pi squared, and that's L over G. Well, this is kind of weird. Now this is a little awkward. We want to get G. Before we wanted to get L, we just multiplied the G over. But if I multiply G over, now it's with all this crap on the left side, so that kind of sucks. There's a bunch of different ways you could go about doing this. Some folks would actually just say, hey, maybe it's kind of math kosher. Your math teacher would probably hate me if I said it this way. If I just flip the top thing and bottom thing here, can't I just flip the top thing and the bottom thing here? Actually, I'm pretty sure you can just do that, but your math teacher would probably think that's like heresy or something. So we'll do it this slightly more math-friendly way, where you still multiply that G over, just like we did in the previous question, kind of right here, but we have G times the period squared over 4 pi squared gives us L. And now the last thing is now I'm going to get rid of all this stuff on that left side by just kind of dividing by the period squared and then multiplying by 4 pi squared. And so really that's going to end up giving me G alone is equal to, and then I'm going to multiply the 4 pi squared over, so 4 pi squared L divided by, and then the period squared. So now we just have to do the math part. So G on this new planet, planet X, is 4 pi squared times our length, 0.15 meters, over the period, 0.75 seconds squared. Hey, it looks like we're going to have meters over seconds squared. The units are going to work. Now, again, did we have to use the mass? No, not at all. The guy right here tells us that the mass does not affect the period of a pendulum. So I gave you some useless information just to kind of trip you up and make you think a little bit. But putting this all into the calculator, I end up getting around 10.5 meters per second squared, or in other words, 10.5 meters per second per second. I know this way looks a little sillier, but what this actually is kind of telling us that on this new planet, you had like a ball and you released it from rest, so V naught is 0 meters per second. It means if you waited 1 second and it's down here and it travels 1 meter, so it goes 1 meter, and now it's down here, that means it's going 10.5 seconds. So it speeds up by 10.5 meters per second. That's how much the velocity changes every second. So just kind of a little Unit 1 throwback. But now this question says 2 significant figures. So how do I round that? Well, that just becomes 11. And it would be 11 meters per second, but again, we cannot put units on this, so it's just 11. So that's it. Hope that made sense. If not, sorry, rip.